Okay, recording is rolling. It's Wednesday, 15 September. So this is my original agenda. I wanted to give you guys a bunch of notes and then do some pre-bio diagram, but I rearranged things a little bit. I'll give you guys a few notes, going to postpone some stuff, and then well, we're going to do a bunch of pre-bio diagrams. I've got a PowerPoint eventually I get towards. Okay? So let's start with this top one, F equals ma. Now you guys know that that's one of Newton's laws of motion, right? You guys remember this is Newton's second law of motion that relates force, mass, and acceleration to each other. Okay? So let's take a look at that. Let's start with that one. Okay. Then I'll eventually work my way towards these other ones. So I actually prefer a different version of Newton's second law of motion. I like it written like this. Acceleration is caused by a net force acting on some mass. Right? I think this actually makes more sense. It explains the physics a bit better. Okay? So what causes things to accelerate? Now, you guys have been working with accelerations for a long time in this class in terms of kinematic motion. Now, you guys know acceleration is a rate change of velocity. But now we're getting into the details of what would cause something to change its velocity. Because you guys know Newton's first law of motion says nothing ever wants to change its velocity. Objects rest want to stay at rest. Objects in motion want to keep going same speed and direction. So if something is changing its motion, what's going to, okay, well, it has to be caused by a force. And Newton's second law of motion, which is this right here, makes that connection. It says, well, the more force, the more acceleration. That's a direct relationship. I guess if you double the force, you're going to double the acceleration, triple the force, triple the acceleration. Yes, yeah. Okay. But acceleration is also inversely proportional to the mass. So the more mass of something is, the less it'll accelerate. Give you guys a quick example. So you guys see these different lab weights right here? We've got a 20-gram weight and 1,000 grams, right? 20 versus 1,000 grams. Okay? So remember, grams or kilograms measuring mass, which in physics represents some amount of inertia that something has. But let me put the same amount of force in both of these. So put some force on this one. It goes flying across the room. Same force on this one. Barely budges. It's really hard to move this guy. Okay? Because this one has so much mass by comparison. Just huge denominator, very, very small acceleration. Okay. Now, you know what you can do is you can modify this and get a slightly different story. You guys remember Paul Hewitt yesterday was talking about the two kids on the island trying to get the Hershey bar? And what they were trying to answer was, well, if you have a couple of objects and you drop them and let them go into free fall, which one hit the ground first? Now, you guys know the answer to that question is they're going to reach the ground at the same time. But you could tell the story through this if you modify it a little bit. You say, well, the net force in this case would be, well, there would only be one force. And so it would also be the net force, which would be the weight of the object. Anything that's in free fall, that's the only force on it, it's just its own weight. And then you divide by the mass of the object. That'll tell you acceleration, which happens to be a special kind of acceleration, which is free fall acceleration. On the Earth, that's 9.8 or about 10 meters per second squared. Okay? And remember, each kid on the island had a different reasoning for why gravity should be different. The first kid was saying, well, if something weighs more, then it should have more gravity, which by itself in isolation would be true. But then you bring in the second kid, and the second kid was saying, well, hold on. More mass means more inertia, which would mean less free fall gravity. Turns out those two effects cancel out, so all objects fall at the same rate. Yeah, there you go. So I said, boom, boom, check those off. Okay. I'll just mention this detail now. This will just kind of come into our notes somewhat organically. If the sum of the forces, that's how you read that, the sum of the forces is equal to 0 newtons, then some object would be in equilibrium. That's all the forces balanced. Like, for example, right now, see this lab weight right here? It's got two forces on it. It's got its weight pulling it down, and it's got a support force from the surface holding it up. That's called the normal force. I guess that, right? But importantly, for now, they're just balancing out. One force down, one force up. It's in equilibrium, like that. Okay. I'm gonna give you guys. Sorry. One more thing. Before I move on, I want to talk about units. So let's look at. Go back to this original form. I think it was MA. Okay. Now, you guys know this is really a net force, right? So if there's multiple forces on an object, first you have to find the net force. Think by doing like tip-to-tail vector addition, something like that. Okay. But let's look at the units. So you guys know that mass in this class is measured in kilograms. It's the only fundamental unit that has the prefix attached to it. Okay. So 1 kilogram, this right here is the base unit of mass in this class physics, the kilogram. You guys know what acceleration is. That's a rate change of velocity, which is meters per second per passing second. That's called meters per second squared. Okay. And you guys know from using these spring scales, if you rerun the spring scales, it says some number of newtons that the force is in. So you put a pulling force, take more force to stretch. the white scales go up to 30 newtons. You can stretch it up to 30, that's 30 newtons of force it takes to hold it right there. So this is measured in newtons. Newtons, right? So now you guys know that 1 Newton that's actually a composite unit. So push or pull measured in newtons is actually some number of kilogram meter per second squared. So when you push or pull on something, you can quantify how hard you push or pull on it in terms of, interesting, this mix of units, kilogram meter per second squared. But this is completely consistent with Newton's second law of motion. So I know we're getting units in this class that look a little bit more involved, a little bit more complicated. All right. I want to take a lot of today to talk about free body diagrams. So let me throw a definition to you guys and then an example. Then I'll give you guys a few notes on friction, and then we'll move on from there. So today we're going to be looking at a bunch of free body diagrams. I've got a PowerPoint for you guys that I also posted on Google Classroom, along with all those new posters. It's all on Google Classroom if you want to do that. Free body diagram is commonly abbreviated FBD because this is a big deal in this class. It's you guys can see this all the time. You guys are going to construct a bunch of these. This is a diagram showing all force vectors on an object. Right? Now there's some other rules that go with this, but when I flip over to the PowerPoint, actually you guys saw the slide when you walked in. Things like you want to draw them proportional, like draw these force vectors proportional. Like if there's one force that's twice as strong, then draw the force vector twice as long. Notice I underlined the word force because these are the only kinds of vectors we care about for free body diagram. I don't care about velocity vectors. I don't care like how fast it's moving. None of that matters to us. All I care about are these force vectors. Okay. So let's look at an example. An example I want to look at is, so for example, let's say you pull a block across a surface. Let's say that diagram, right? Pull a block across the surface. Right? And you guys did this the other day. Right? You guys, I had you remember during this sandbox type lab, did like 10 mini labs, and one of them involved exactly what I'm going to show you guys here. Say if you lift a block versus if you drag it across the surface, and then you recorded the numbers. So show a free body diagram for this and analyze what was going on with that motion. So maybe there was a table surface. It could be the table surface right there. There's a block on the surface. Well, one of these lab weights, right? Here. And then what you guys did is you hooked up a spring scale, just started pulling across the surface. Something like this. Start pulling across the surface. Right? So throw a center of mass dot on that block. Okay. And then let's think about what forces are on this block. Okay. Well, it's got a weight pulling straight down. Okay? A weight pulling straight down. Okay. And I can label that. Okay. Well, let's go back here. Okay. You guys remember a few minutes ago I told you that here's the Paul Hewitt story. 2 kids on the island chasing that Hershey chocolate bar. Okay. See, if you rearrange this, cross multiply at the m, look what you get. You get weight is equal to mg. You guys see that? Okay. Now, careful about this. Mg in a different context. As a unit, it might be like milligrams if you're like taking medication or something. Okay. That's not what it means in this class, in this context. These are 2 variables multiplied together, not units, variables. Okay. Mass times gravity. Okay. So weight. You can also represent weight as F sub g. I prefer mg. I've just done that forever. So I'm going to label this mg. There's some number of newtons that's pulling down. Now, if that's the only force vector I had on that thing, then I would be saying that it's in free fall, kind of like I toss it off the edge of a cliff and it just goes into free fall. Obviously, that's not what's going on here. This is in equilibrium. The forces must balance. It's just sitting there. So there's a support force from the table, and the support force has a name. It's called the normal force. So I'll label this F sub n. Notice how I made that the same magnitude, right? So the weight down and the support force up. So this is called the normal force. Now, why is it called normal? Does anybody happen to know from a math class maybe what the word normal means? But like if two lines are normal to each other, they're what? Perpendicular, right? Perpendicular, right? So the word normal means perpendicular. And perpendicular to what? Perpendicular to the surface. See how this support force is perpendicular to the surface? That's such an important property of that support force from the surface that it's pointed out that it is, that's the name of it. It's like the perpendicular force, the normal force. Quick flash forward here. I'll show you guys an example that you've seen here and there, like throughout the class so far. You guys remember a weight sitting on an incline? Now, you guys started off just saying, okay, the weight's pulling straight down. Ooh, look at that, mg, that's the weight. Then you guys split this into components. Now, you guys have known that for many weeks, how to take a weight vector on an incline, split into components. But now we're adding to the story. We're saying, well, that's not everything that's going on, because otherwise this block would be in free fall. There's some support force from the surface that's pushing it, well, kind of upish, but it's not straight up. It's this vector here. See, this is labeled F sub n. That's the normal force. And look at the direction it's going. Is that going straight up against gravity? No. It's going perpendicular to this surface. Guess that? In fact, if this incline were even more steep, what if this, just eyeballing this looks pretty close to about 30 degrees, I'm guessing. Right? But what if it ramps up to like 80 degrees, just something crazy steep? Could you imagine that the support force is probably getting pretty small? And if it was a vertical wall, you put a block against, it's just the support force is going to go to zero, something like that. Right? So yeah, that's what that looks like. So eventually when these become more complicated, you guys are going to see that come back. But for now, we got a nice flat surface and it's perpendicular to the surface. All good. That's it. Okay. But I said we're pulling a block across the surface, right? So there's got to be some more forces. So let's get those on the board. Maybe I'll have an applied force, say, going to the right, maybe something like this. I'll call this F sub pull, like a pulling force. Right? So I'm taking that spring scale, I flipped it to the lab weight, now I'm just like pulling this across. Now there's probably some kind of resistive force, maybe like a friction force, something like that. Okay. So let me add to the premise. Pulling across the surface. Okay. What if I specified at constant velocity? Okay. Now, you guys know constant velocity, that means the acceleration is equal to what? Zero, right? Constant velocity, there's no acceleration. It's not speeding up or slowing down. It's just, right? And if there's no acceleration, there's no net force, right? Which my diagram doesn't exactly show. My diagram actually is showing a net force. So that means I'm missing something. I'm missing a friction force. So I'm going to draw that exactly opposite of the pulling force. I'm going to label this F sub FR. Okay, this is the friction force. And I'm going to tell you guys a few things about friction force, but I guess for starters, it's good to know that friction force always opposes the direction of motion. Okay. So for free body diagrams, remember I told you guys that velocity vectors are not part of free body diagrams, only force vectors are. Okay. So sometimes that sets up some kind of ambiguous situation. Is something moving or is it at rest? Sometimes it's ambiguous, you can't really tell. Okay. But if you can identify the direction of a friction force, then, okay, in this case, you actually would know that this block is sliding to the right or being pulled to the right, if it's static, something like that. Yeah. You guess that? So I'll draw a little velocity vector, but it's not actually part of the free body diagram, though. You guys good so far? Tell you guys a bit more about friction. So it turns out that there's actually different kinds of friction. And I can show you guys by going back to, by hooking this up. So see if I pull this, when I start pulling this, take a look at this ratio. You guys see there's, during this first few newtons, the block doesn't move at all, right? So I can pull for a few newtons and it doesn't even budge. You guys see that? In fact, the harder I pull, do you think the friction force just responds and builds up at the same time? You guys imagine that? Right? And then at some point, it finally does break the friction, starts to slide, but it takes a while to get back on. Okay? So that initial part where it's all just static, that's called static friction. And then once it starts sliding, it's called kinetic friction. And I'll tell you a few details about that. So static friction is when the two surfaces are not yet sliding past each other. Okay. And then kinetic friction is when they are. So let me leave some space on paper. I'm going to give you guys an equation, but so then leave some space. Kinetic friction is, well, the opposite. Okay. So the two surfaces are sliding past each other. Now, in the case that two surfaces are sliding past each other, I can give you guys an equation like this. The friction force, turns out, is equal to coefficient of friction times the normal force. Okay? You guys know what normal force is. That's the support force that's perpendicular to the surface. Okay? And then, see, there's some friction force that results from that. What is this guy here? I'm going to throw a little subscript K on that. I'm going to call this is the coefficient of kinetic friction. Okay. And it's some material property. So if I have this weight, pull across this paper, well, this weight's painted in some kind of black paint, and it's on this paper. So the paint against the paper, there's some material property that tells that could govern like how much friction is going to result from that. Okay. You can rearrange this equation and say coefficient of kinetic friction is equal to friction force compared to normal force. Just divide them out. Okay, is that? Okay. And I want to give you an example that relates to this last free body diagram that I just drew, which is that, put some example numbers on here. You guys know this 1 kilogram mass weighs about 10 newtons. So let's just, example numbers calls about, not right very well, calls about 10 newtons. If that's 10 newtons, then the normal force would also be 10 newtons just to hold it in place, right? Okay. And let's say that I was pulling with, okay, just make up a number, let's say like 3 newtons. So let's say a pull was like 3 newtons. Okay. Well, one more thing you would know is, remember in the premise I told you constant velocity? If that's also true, then wouldn't the friction force also have to build up to 3 newtons to balance it out? Was 3 newtons in that case? Okay. So everything's balanced out, right? 10 down, 10 up, 3 to the right, 3 to the left. This block would be in equilibrium, which doesn't necessarily mean that it's at rest. In this case, it isn't. It's actually moving. It's just moving with constant velocity. Okay. So how does that compare to these notes here? Well, put these side by side. Right. I just told you guys friction force, for example, could have been 3 newtons. Normal force would have been 10 newtons. So the coefficient of friction would be 0.3. It says 0.3, like that. Or if you thought about it in this way, if you knew the normal force is 10 newtons, multiplied by a coefficient of friction of 0.3, you should get 3 newtons out of that. Guess that? Good so far? But there's a reason I left a space here, because I want to look back. Well, what about this other kind? What about before it ever broke the friction at all? And the reason I want to come back to it is because this is slightly trickier to think about. Reason being that there was that initial period where, oh look, remember there were all these different forces before it broke the friction initially, right? There's like, half a Newton, 1 Newton, whatever, something like that. Okay, before it ever broke the friction initially. So I can create basically the same equation. I'll say friction force equal to coefficient of friction times normal force. Except that this is now going to be static friction, and I'm going to change this equal sign to an inequality. I'm going to say it builds up to that point, represented by less than or equal to. So the friction force can go up to the certain value. So you guys know that this mu sub s represents coefficient of static friction. Okay. So the idea is that there's some initial friction that you have to do to overcome. There's some initial friction you have to overcome to get it to slide. Okay. Once it breaks that friction, then it goes to a kinetic case. Okay. But before it builds up to that point, it's like you have to push or pull, hard. In this case, I'll push with my hand here, right? I'm pushing harder, and the friction force building up, and finally it breaks, and then this thing can slide across the paper, and then that becomes kinetic. Okay. You could rearrange this if you want to. Again, mu would be just same idea. It's a fraction friction force divided by normal force. Okay, so far. Right. Tell you guys one more thing about friction, and then we'll go make some free body diagrams. Okay. So comparing these two coefficients of friction, we got static versus kinetic. Okay. I want to make a graph to tie this all together. So let's do two surfaces slide past each other. I'm going to do a velocity versus, the coefficient of friction versus velocity graph. Okay, kind of a weird graph, but so coefficient of friction versus velocity. So velocity, the two surfaces moving past each other at some speed, like meters per second, something like that. Okay. And you guys know this stands for coefficient of friction. Coefficient of friction. Okay. Now, when the two surfaces are not moving past each other, wouldn't that be zero velocity? Okay. There's a coefficient of friction to overcome that initial friction before the surfaces break. Okay. And that's called static friction. So I'll label that point mu sub s. Now, once the two surfaces are sliding past each other, then what you'll notice is that, weirdly enough, it turns out it doesn't matter how fast they're moving past each other. That it's pretty much like the same coefficient over and over again. So it's just a horizontal line. And then, see, once you break that friction, it just jumps down to that value. Okay. And that value is called coefficient of kinetic friction. Okay. Notice I said it jumps down. That's pretty much universally the case. So you guys know that coefficient of kinetic friction is less than coefficient of static friction, which is some number greater than zero. Okay. I'll give you guys some example numbers. So for example, let's say this might be 0.50, this might be 0.25, and then a frictionless surface would be like an air hockey table. You guys ever played air hockey? It's basically a frictionless surface. That'd be like if you had a coefficient of friction that was exactly zero, something like that. So in this case, like for example, this might be 0.25, this might be 0.50. I think this is the first number in this class that you guys have ever seen in this class that does not have a unit attached to it because it's newtons per newton. If you go back and look at notes from last page, newtons per newton, the newtons cancel out. Okay. So this is actually a unitless value, isn't it? Guess that? All right, questions so far? All right, so friction's going to come back. I just wanted to plant some pretty fundamental ideas right here, and we'll look at this later. I've got a lab signed up for you guys. And there's other kinds of forces I also want to talk about, but I think that's plenty enough to digest for right now. So let's flip over to look at free body diagrams. Let me present screen 2, share. Okay. Look at a bunch of free body diagrams here. All right, so I guess that was when you walk in. Free body diagram is just a diagram showing all the forces acting on an object. Draw force vectors to represent relative magnitude and direction of each of the forces. Right? Like in the example on the right of the screen there, the weight is down, the normal force is acting up. I drew those as the same length arrow because they're the same magnitude vector, so that block would be in equilibrium. Okay. A rule with these vectors is always connect the tails of vectors to the center of mass and draw the force vector extending away from the object, just like I did in that example. Remember that forces are measured in newtons, And force vectors are not these other kind of vectors. So velocity vectors, acceleration vectors, displacement vectors, don't draw those in free body diagrams because they're not part of the diagram. The only vectors that count for free body diagrams are force vectors. Okay. Good stuff. Right, let's look at some examples. Block at rest on a table. Oh, well, you guys know that one already because you just saw that one. So 2 force vectors, that's it. Block at rest on a table. There's the weight pulling down. There's the normal force acting up. I guess the implication here is it's a horizontal table, flat table, but it's usually the case, right? So let's get that one. What about this? Next one. What if there's a block at rest on a table, pushed horizontally, but with not enough force to overcome the initial friction force between the block and the table surface? Okay? This is one of the reasons I gave you guys some notes on friction so that you'd be thinking, okay, well, I know a bit how friction works. Well, let's see. Block at rest on a table, so it must have a weight pulling down. Right? I mean, if it didn't have weight, none of these other forces would exist because imagine if you're in the International Space Station, everything would just be kind of floating around. So we're gonna get that one to kickstart us off. Right? But there's a table that's holding it up, right? Like that support force. So that's called the normal force. So got that one. Right? It looks like in the premise up here in the white text, it says you're pushing horizontally. So it must be an applied force, like a pushing force. Let's say you're pushing off to the right here. Is that right? Now, if that's all you drew, if you just drew those 3 vectors and walked away, would that satisfy this premise up here? It would not. And the reason it would not is because, see what it says, with not enough force to overcome the initial friction between the block and the surface? Right? Well, this block must still be at rest, which that free body diagram doesn't yet show. So I've got to include one more force. It's that one right there, the friction force. Right? Now, in this case, that friction force happens to be static friction because that initial friction has not been broken yet. Is that? How about next slide? What if there's a block on a table and you're pushing it horizontally so that the block moves with constant velocity across the surface? Okay, so we got the weight pulling down. We got the normal force holding the block up. That's a support force from the table. We've got an applied force, say, pushing it to the right. Okay? And I still need a friction force because of, you guys see this term here, constant velocity? Okay? Constant velocity, that means that there's no acceleration. If there's no acceleration, there must be no net force. So all the forces have to balance. Right? Constant velocity, equilibrium. Right? And if you look at that diagram right there, doesn't that free body diagram look exactly like the previous one? Let me go back to last slide. Last slide said, look at this, it's the same diagram, but the block was at rest. That's interesting. So block at rest, which is right there, or next slide, a block sliding at constant velocity, they have the exact same free body diagram, don't they? Okay? So if all you had was the free body diagram and you were not told if this was static or kinetic friction, and I didn't draw that very helpful velocity vector off to the right that's not actually part of the diagram, you wouldn't actually know. You wouldn't know, is that block at rest or is it sliding, right? So it would be pretty ambiguous, wouldn't it? So you'd have to be given that detail. How about this? Next slide. What if you push the block horizontally so that there is a net force? What would that look like? So it's got its weight down, it's got the support force from the table up, it's the normal force, right? Now we're gonna push, let's say you push pretty hard so that it's more than the friction force. You guys see now that there's a net horizontal force, right? Isn't that block accelerating to the right? It sure is, isn't it? Right? Now, normally I would say accelerating to the right could be one of 2 things. It might be speeding up to the right or it might be moving to the left, slowing down. Except in this case, it actually is not ambiguous. And the reason is because of one more detail that I told you guys earlier. Remember I told you guys that friction force always opposes the direction of the motion? Okay? So in this case, you know that the block actually is physically moving to the right and speeding up because you know that because the friction force opposes the motion. Okay? Right. How about a rock in free fall with no air resistance? Rock in free fall. Draw this one in your notes before I show you the answer. I want to see if you guys can get this. I bet you guys can. You should be able to get this. Rock in free fall. We're going to ignore the air drag. What's that going to look like? All right, so this rock has a weight that's pulling it down. So label that mg. Remember, that's the force from Earth pulling you down. Okay. Anything else? Nope, that's it. That's the entire answer right there. That's the entire answer. Okay. Whenever something's in free fall and when something is in free fall and you are ignoring air drag, then that's it. It's just under the influence of only one force, its own weight, and end of story. Right? And if you divide this weight by its mass, you get g, which will tell you the acceleration. That's it. Okay. Next slide. Let's put the air drag in. This is something we haven't really touched so much in this class. Rock and free fall with air drag, but before terminal velocity. Okay, so we got some new ideas popping up here. Do you guys know what this term means, terminal velocity? I bet some of you guys do. Who can tell me, what is terminal velocity? Does anybody know? Okay. How about this? If we're starting to include air drag, do you think that the faster you fall, the air drag is going to build up more and more and more? It kind of makes sense, right? Do you think at some point that air drag can build up so much that it actually bounces out the weight pulling down? Right? Could do that, right? So yeah, we'll get to that case. I want to explore that case a little bit, but first let's get this free body diagram. Think what this look like. Okay. So obviously we got the weight pulling down because you threw this thing off a cliff. So this weight's pulling down, making it accelerate. And it looks like the air drag is building up, but notice that I made the air drag smaller than the weight. You guys see that? So this rock right here falling, is it in equilibrium? What do you guys say? No, it's not in equilibrium. There is a net force on it. The net force is downward because the weight is more than the drag. There is a net force. Now, is it still accelerating at 10 meters per second squared? Ooh, not anymore. The acceleration is going to be less because the net force is less than its weight. Then you divide by its mass. The overall acceleration might be, maybe like 5 meters per second squared, something like that. Right? It's accelerating less. Huh, interesting. Okay. So it is picking up speed. Hey, the fact that it's picking up speed, do you think that drag force is also going to continue to increase? Kind of makes sense it would, wouldn't it? I'm going to flip my screen over. I'm going to give you guys a little bit of context into air drag. Now, this is sort of beyond the scope of this class, so you don't have to memorize what I'm about to show you guys for any quizzes or anything. You're probably not going to ask this, but it does give some context for what I'm about to show you guys, which is, let's say you got some object, right? Like this rock, falling straight down, right? Rock and free fall. And okay, so it's got its weight pulling down. Maybe it's got a drag force acting upward. Call it force drag, like air drag. Okay. I wonder what that air drag is equal to. Okay. There's actually an equation that goes with it. I've seen slightly different versions of this. I'll throw you guys one version of it. Okay. I've seen something like this. Okay. So I'll tell you guys what all these little parts mean. Okay. So this is a coefficient of drag. Think of it kind of like coefficient of friction. It's something you could maybe experimentally measure, right? I don't really want to focus on that so much. This Greek letter rho looks kind of like a curly P. In this context means density of the fluid. How about this? If this rock were falling through air versus falling through water, do you think the drag force is going to be a lot more through the water? Yeah, a lot more. Right? In fact, it's going to be about 1,000 times as much because water is about 1,000 times as dense as air. Right? So 1,000 times the density, 1,000 times the drag. Right? What do you think that this A stands for? This A is actually why you would wear a parachute if you ever jumped out of a plane. Here's a hint. Okay. Cross-sectional area. Okay. Here, I'll show you guys why it's a good idea to wear a parachute. So parachute is this guy who's got a little parachute backpack. As this guy's falling, I bet his free body diagram would look a lot like for this falling rock. Right? And if you want that drag force to build up, then look at this huge cross-sectional area right here. This cross-sectional area of this parachute. Would you want to jump out of the plane with a parachute that's the size of a paper cup? That'd probably be a terrible parachute because it has such a small cross-sectional area. Right? That's not going to give you very much drag force. And then finally, this is the part that I actually want to hone in on. The reason I'm throwing this up here. That V, you guys know in this class, could stand for speed, how fast you're moving through the air. Okay. So as you go faster, 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 the drag force builds up and up. Interestingly, it's a squared relationship. So if you like double your speed, you actually have 4 times the drag force. If you triple your speed, you have 9 times the drag force because the speed coefficient gets squared. Guess that? But the takeaway that I want you guys to see is that faster you're going, the more the drag force is going to build up. And at some point, it's going to balance out with your weight. When it does that, I think it's the next slide on my PowerPoint, so eventually work towards there. When it does that, though, you would go into equilibrium. Just go down at a constant pace. Here, when I'm on the projection side, though, do another graph. Let's do for free fall, but there's also air drag. So label this free fall, or maybe I should say like throw a rock off a cliff, something like that. Let's look at your speed as a function of time. So speed in meters per second as a function of time in seconds. Now this is a graph you guys have seen many times. Some of you guys got this graph on your quiz or something very similar to it. What does this look like so far in this class? You guys have drawn this many times. Let's say you drop a rock off the edge of a cliff. Going to do just something like this, right? It picks up the speed of 10 meters per second per passing second. So the slope of that is g. Right? Now the catch is that that's only true if there's no air drag. So like in a vacuum, no air drag. The trickier question is, well, what's a more realistic version of this graph if you put the air back in? So you guys know this. The faster you're going, the more the air drag is going to build up. It's going to get bigger, bigger, bigger until it eventually balances out with your weight. And when it balances out with your weight, that would give you 0 net force, which means no acceleration, which means you stop accelerating. Can you guys draw what the curve would probably look like once you include the air and the air drag? What you guys think about that? I'm going to flip back to that in a minute. See if you guys can draw that, figure it out before I show you the answer. Oh man, it's going to happen again. All right. Yeah. Let me flip back and forth real fast here. All right. Usually if I do this, this resolves this problem. Okay. Maybe like that. Right. Now, hang on. Yeah, you guys figure out what that graph probably looks like once you include the air drag? Okay, so back here. Okay, so no air drag looks like that. Right. With a little bit of air drag, it could look like that. That was the last slide you guys saw. Right. Now this slide, rock is in free fall with air drag, and it's reached. You guys see that term, terminal velocity? Has that term come up in here before? Terminal velocity. Right. What does that mean? Terminal velocity. Speeds pick up to a speed so fast that those forces will balance with each other. It will go into equilibrium. So when it does that, now I'll make the answer graph. Did you guys come up with something that looks like maybe something like this? Okay. I'm going to make a mark right here, make a horizontal asymptote. I'm going to call this V terminal. That's a terminal velocity. Let me write that a bit bigger. This is called terminal velocity. And the actual curve then would look something like this. So you jump off the edge of a cliff, and you start free falling pretty close to what we would predict with the equations you guys see so far in this class. Then the air drag starts to build up, so you don't go quite as fast. Right? And when you've been falling for a long time, let's say you like jump off like Mount Everest or something. Right? Then eventually you'll approach this horizontal asymptote, and you're not going to go any faster than that. Now, what is this number? Well, it depends on your shape. That's why there's some other parts to this drag force equation, right? Like, for example, the size of the parachute. If you have a very large parachute, you're probably this terminal velocity is going to be lower. Right? And if you had no parachute at all, well, you would reach terminal velocity, but it would be much higher value, sliding to the ground a lot faster, something like that, right? But you'll have a curve that basically takes some version of that shape. All right, let's look at what would be the free body diagram for, oh no, okay, gonna make this happen. For terminal velocity. Luckily, I only do a couple of PowerPoints in this class, so, okay. I think I may have figured out what's going on. Maybe it doesn't like flipping over in presentation mode. Okay. Okay. Here we go. Okay. So rock and free fall, but now let's put the air drag in there. Let's take it all the way to terminal velocity. Okay. So that'd be something like this. So it's picked up to such a speed that air drag bounces it off. Okay. And then the fact that those forces balance means that there's zero net force, there's zero acceleration. It'll just go down at constant speed all the way down to the ground. Next one, a boat moving through water at constant velocity. Okay? So I put a velocity vector, but it's not actually part of the diagram, right? I'm just saying direction of motion. So this boat has a weight pulling straight down. This boat has a buoyant force holding it up. Okay. Now that buoyant force is kind of like the normal force, right? That's just from a fluid. Okay? There's maybe an applied force, maybe the propellers pushing against the water that would propel the boat forward. Right? And then there's going to be a drag force from the water. In fact, the only reason that I put the direction of motion of the boat, like that green velocity vector, is so I can point out that the drag force is going to oppose that motion. Okay, that's no reason. Let's do a couple more of these. Can you guys figure out a way to draw three forces so that they're in equilibrium? So we're a little bit, I know, got a couple minutes left in class. I hate to do this, but I'm going to show you guys the answer. There's actually many different answers. There's some possibilities. The one on the left, actually, you guys sort of saw yesterday. If you turn the one on the left upside down, it's not like there's a weight pull down, spring scale pull up left, up to the right. It's maybe 10 newtons, 10 newtons, 10 newtons. Right? Or the one on the right, maybe have 10 newtons up and then 5 and 5 down. Right? Here's a parachuter before terminal velocity. Here's a parachuter at terminal velocity. Right? Same idea. It just goes down at constant speed in that case. Okay. And then the last one we'll look at today. Can you guys imagine what would rocket just screaming through space, constant velocity, 10,000 meters per second? What force is on that? Hang on, isn't that what the Voyager spacecraft is doing? It's just screaming through space at a constant velocity? Are there any forces on that rocket at all? No. That rocket is only moving because of inertia. See constant velocity. See, if that rocket turns on its boosters, then that would cause it to accelerate, wouldn't it? Which would destroy this constant velocity condition. So that's it. That rocket is only moving because of inertia, and there is no force at all. So there's no force on that diagram. We're about halfway through this PowerPoint, so I do want to do some more of these with you guys tomorrow. So that's what we'll do, and give you guys a few more notes tomorrow.